So now we want to define very basic concept. So again, we are studying about graphs. And graphs is a collection of binary relation among objects. And to make it more rigorous, we define it. So we mathematically define it. We say that a graph is G. Usually we denote as G as the first letter of graph. This is mathematically a pair B, E, where this V is usually we denote as V of G is a set of vertices. So we call them vertices. These are the dots that we saw before. We call each dot as vertex. And this E, which we write as E of G, is a multiset of edges. And these edges are the line where this on edge is a set of at most two vertices. So this name of vertex and edge comes from, the usage of graph. In many cases, we consider this like tetrahedron or cube. So we consider this kind of polyhedra. In many cases, we draw this polyhedra on a paper, then what we get is a graph. And we have dots and then line between them. And in this polyhedra, these are called the vertices, which is the place where it's very sharp. And these are the edges, which are shared by two faces. So hence we get this name of vertex to denote the dots, and edges, which denote the lines between two vertices, which are paired. And we call, there are many useful concepts. When we use this absolute value sign of G, we denote it as the number of vertices in G, and we call it as the order of G. And we write E of G, which is the number of edges in here, and we call this the size of G. And for notation, we use this bracket notation, bracket n for certain natural number n denotes the natural number between 1 and n. And we simply write uv to take the edge, which consists of u and v. So this is same as pu, as it is a set of two vertices. So in this aspect, if we go back to this graph, and this is what? This is pair ABCD. Maybe let me move it here, comma, the collection of edges, AB, multi-set of edges. There are two edges between A and B, AC, AC, CD, AD, BD. So this is B of G, and this is E of G. And then this pair represents this graph. And now seeing this graph again, you can notice one thing. If we consider certain problem like matching problem or coloring problem, in those natural, problem, having two edges here or one edge here makes no difference. If you want to get to somewhere, and while doing the using this edge and using this edge makes no difference as long as we just consider getting there. In other scenario, maybe this edge and this edge, this bridge and this bridge provides the different speed of moving there. So it might make difference. But if we just care about whether we can get there or not, the possibility of getting there, regardless of the time constraint, then those are identical. And finding matching, again, when we match here these two pairs, whether we match it through this edge or through this edge does not make any difference. And giving red color, blue color here, if there is an edge, they are conflicted, so we want to give different color. Again, having two edges or one edges makes no difference. So in many natural situations, those does not really matter. So having multiple edges between them, so here we define it as a multi-set of edges. So having multiple edges between them can be happening here, but for many situations, those are again redundant information. So we want to give the names of the graph which does not have those things, which we call simple graphs. So, for example, again, we give the name of those. Say first, a loop is an edge of size 1. So here, if you see, an edge is a set of at most two vertices, right? So there could be one vertex edge. And what's the case? That's the case where there are like a connection between a dot and itself, a vertex and itself. It could be the situation. There could be a bridge here on the land, and then you want to insist to cross it. Yeah, that's where this loop name comes from. And we say this is an edge of size 1, and we say a multiple edge is an edge appearing more than once in a graph. And we say that a graph is simple if it does not contain any loops or multiple edges. So throughout this course, if we don't state it, we always assume that all graphs are finite simple graphs. We always assume that all graphs are finite simple graph. So if we say something is a graph or a graph is given, then we always assume that this is finite simple graph, meaning that the number of vertices is finite. And there are no loops and no multiple edges. So this finite means that this order of G is finite. And if we have to mention about non-simple graph, we use different terminology. We say multigraph. Okay, and there are additional terminology. We say that the vertices U and V are adjacent if UV is an edge of G. So if they are connected, we say they are adjacent. I mean, connected by the line. Those two dots corresponding to the vertex are connected by the lines, which are the edge between them. And we say a vertex U and edge E are incident if E contains B. And we say two edges E and E prime are again incident if they share a vertex. Their intersection contains at least one vertex. And we say that U is a neighbor of V if, again, UV is an edge in G. And we say that if there is an edge between U and V, then U and V are endpoints of the edge UV, which is in the graph G. And we write the capital N sub G of V is the set of neighbors of V. Oftentimes I just write NVR instead of neighbor. And also just write BTX instead of vertex. And we often omit this G if the graph G we talk about is clear from the context. We just write NV. And we also write D of V. So again, the subscript G we often just omit. This is the what we call degree of V, which is the number of edges incident with V. And we count a loop twice for this purpose. But for most of the time, we consider simple graph. the degree is same as the number of neighbors would be. So we do this because, for example, if you have in multigraph, if you have these edges, so if we zoom in and then see this picture, then you have one vertex and then 4 lines coming out. And again here, one vertex, 4 lines coming out. In terms of, say, you study about topological graph theory, or assuming this graph as a drawing on certain space, these two situations are locally like isomorphic. Then we want to count the edges attached to this here. In here it's 4, 1, 2, 3, 4. Here 1, 2, 3, but we want to count the loop twice to make it like isomorphic in this local sense. That's one intuition. And the reason why we call this degree is roughly, I mean, one of the ways to tackle the four color problem was that if you have a graph G, then we have a U, V, W, G as a vertices. Then you have this graph. Then what you could do is you introduce the variable XU and XP, and then you subtract it for each edge. XU minus XW, XU minus XG, XP minus XW. And what's the coloring? Coloring is that you assign certain value in this variable so that this becomes non-empty. So this value is assigned, and then this is non-empty means that none of these are 0. That means all value assigned. So let's say this is okay. So these two are assigned the same value, but all the adjacent pairs get the different value. So this is same as the graph coloring. So you can tackle this graph coloring by studying this polynomial. In this polynomial, what's the degree of this variable? That's exactly the number of edges incident with it. So hence the name degree comes from. Anyway, this was one way to tackle the four color problem by studying this polynomial, which is called chromatic polynomial. So we have defined the basic definitions of graph. And in the next video, we will define graph isomorphism and subgraph, which are very natural.